Hi, Assalamualaikum and a very good morning. So now we're going to do some tutorial discussion for chapter 3. And now we're going to focus on both of the subtopic, which is the subtopic of 3.1, classification of element, and the subtopic of 3.2, periodicity. And now we're going to focus on this question here, which is tutorial question 1, 2, 3, 4, 6, 7, 8, 10, and 11 respectively. So without any further ado, let us start. So for tutorial question 1, we need to state the period, group, and block for each of the elements here. So we are given the electronic configuration for each elements. So for this reason, we're going to use the table in order to answer that. Okay, so as usual, you can always start up with a PUBG method. Okay, so the PUBG method is you need to look at the period first, and then you determine the block, and then you can identify the group. Okay, so for element A, you have a configuration of 1s2, 2s2, 2p6, 3s2, and 3p6. So from this configuration here, you know that your period will equal to the highest principal quantum number, which is 3. And then from the valence electron here, which is n equal to 3, you know that from the configuration, which is ns2 and p6, it refers to the p block. Okay, and in this p block, it's going to have 8 electrons. Okay, 8 valence electron. So the 8 valence electron will help us to determine the group. Okay, however, since it is located in the p block, we need to add up with 10. So the 8 electron plus 10 going to be inside group 18. Okay, now we're going to use the similar method for element B. So for element B, the highest principal quantum number is n is equal to 4. So it is located in period 4. And because it has a configuration of ns2, it means that it is located in the s block. Okay, and in order to determine the group, we need to determine the valence electron. So in this case, we have the valence electron to be 2. Okay, and this is inside the s block, so we don't have to add up with 10. So we can just directly say that it is in group 2. For question C, we need to look at the configuration here, which is 1s2, 2s2, 2p6, 3s2, 3p6, 3d3, 4s2. So their valence orbital is to be here. Okay, and the highest principal quantum number going to be n is equal to 4. So it is located in period 4. And if you were to look at the configuration, it's going to be n minus 1, d3, and s2. So when you see this kind of configuration, which is n minus 1, d, and ns, you know that it is located in d block. Okay, so since it is located in a d block, so you can say that d block here, and then you can also determine the valence electron. So for d block, the number of electrons in the d orbital is add up with the s orbital here. So the total number of valence electron is 3 plus 2 going to be 5 valence electron. And this 5 valence electron going to determine the group of the element C here. So similarly for D, we're going to have 4s2, 3d, 7. So the highest principal quantum number is 4, which is n equal to 4. And then your block here is similar to this configuration here, which is n minus 1, d7, and s2. So when you see this kind of configuration, okay, and here equal to 4, and 4 minus 1 equal to 3d. Okay, so the 3d and 4s can be interchanged, so it's depending on the question. So n minus 1, d7, and ns2, you know that it is located in the d block. And in order to determine the group, we can look into the valence electron. So 7 plus 2, we're going to have 9 valence electron. So it is located in group 9. Okay, so this is how we're going to do tutorial question 1. For tutorial question 2, the table below shows the group and period of element P, Q, R, and S. So for question A, we need to write the electronic configuration of all the elements here. So for element P, you know that it is located in the period 2. So logically, the highest principal quantum number here should be 2. So if you were to write the electronic configuration, you're going to do 1s2, 2s2, okay, because it is in group 16. So you know that you need to continue to P4 here. Okay, so if you were to go back into this one, you can convert it to the same information. So from here, you know that your period is equal to 2, and then it is located in the P block because you have NS2 and P4. And then if you were to find out the group, it's going to become 2 plus 4, which is 6. And then you need to add up with 10, which is 16. So you know that the configuration here is correct. Okay, and now you're going to do the same for Q. So you know that group 18, which is in the P block as well. So you know that Q going to be 1s2, 2s2, and then because it has 18, is in group 18, so you know that it's going to have 8 valence electron. So from here, you know that N, which is the period, going to become 2, and then the block is in P block, and then the valence electron is 2 plus 6, which is 8, and then this is going to plus with 10 because it is in P block, and hence you're going to get group 18. So you know that your Q here is correct. Okay, and now you're going to do for R as well. So R here will have the highest principal quantum number 3, and then it is located in group 1. So you know that it is in the S block. So basically you just start it until you stop to 3. So 1s2, 2s2, 2p6, 3s, because it is located in 1, so it will stop at 1. Okay, so to double check, you can say that the R here will have a period 3, and then it is in S block because it is an S1, and then it have group 1 because of the 1 valence electron. So you know that the answer here is correct. Okay, and for the S here, it is located in period 4, so you know that the highest N going to be 4, and then it is located in group 17. Okay, so you're going to have 7 valence electron. So it's going to be 1s2, 2s2, 2p6, 3s2, 3p6, 3, 4s2, 3d10, and then 4p5. Okay, because we're going to have the configuration to be ns2 and p5 here, where n is equal to 4. Therefore, we're going to get 4s2, 4p5. And the 3d10 here is just fulfill orbital. And this is the outermost orbital, which is for s2 and 4p5. So we know that it is located in the p block. And then the number of valence electron that we have is 2 plus 5 going to become 7. And since it is located in the p block, it's going to add up with 10. So we're going to get group 17, which is similar to here. So we know that this one is the correct answer. So S going to be 1s2, 2s2, 2p6, 3s2, 3p6, 3d10, 4s2, and 4p5. And this position here is interchangeable. Okay, and usually we're going to write 4s2 first, then only 3d10. Okay, and then for B, we're going to write the molecular formula for the compound form when P react with R. So your P here will have, okay, so we need to find the molecular formula. So you know that it can form an ion. For example, 2p4, in order to become stable, it needs to become 2p6. Okay, so it's going to receive 2 electrons. So it's going to be p2 minus. Okay, because when it goes to 1s2 to s to 2p6, it's going to have 10 electron. And this 10 electron here refers to the noble gas configuration, which is neon. And for that reason, the p element here need to receive 2 electron. And for the r here, okay, so in order to be the stable octet, it need to donate 1 electron. So you're going to become r plus. So if you were to write the molecular formula, you're going to get p r2. Okay, so the answer is going to be pr2, or you can also write it as r2p, because usually metal we're going to write it first. Okay, now for tutorial question 3. The figure below shows the location of elements A, B, C, D, E, and F in the periodic table. Which of the elements are metal, non-metals, and metalloid? So the metal will usually be in this group, which is group 1 and 2, usually including the transition element. Okay, so for group 1 and group 2, we're going to have A, B, and E as the metal. However, the A here is hydrogen because it starts up with a first proton. So you know that the hydrogen is located here. So hydrogen is not a metal. So for this answer, we only get element B and element E as the metal. For non-metal, it usually located at this part here. Okay, so the metal that we have, the non-metal that we have is C and element D here. Okay, so this include C, D, and A, which is the hydrogen. And for the metalloids, we're going to have the F here. Okay, so F here is usually located in group 13, which is metalloids, or known as the semi-metal. And now we need to arrange the element B, C, D, and E in the ascending order of the atomic radius. And then we need to explain. So only for element B, C, D, and E. So from here, you know that obviously E gonna become the largest because it has the highest principal quantum number, n equal to 2, and here is equal to n equal to 3. Okay, and B, C, and D here is located on the same period. And as what you know that across the period, the proton number increases. So when the proton number increases, the ZEF increases as well. So when the ZEF increases, the attraction between the valence electron and the nucleus will be increasing as well. And as a result, the size gonna decreases across the period. Okay, so when the sizes decreases across the period, you know that D gonna become the smallest one. Okay, so D gonna become the smallest, followed by C, followed by B. Okay, so the answer that you're gonna get is to be something like this. So you're gonna say that E gonna be greater than B, greater than C, then greater than D in terms of the atomic radius. So you can say that E has the largest atomic radius because it has largest screening effect, where n is equal to 3. And E has the highest possible quantum number compared to B, C, and D that only have n equal to 2. And B, C, and D are in the same shell or in the same period, which is n equal to 2, but the proton number increases from B to C to D. So the effective nuclear charge also increases. And the attraction between nucleus and the outermost electron became stronger, and hence the atomic radius decreases from B to D, where D here is the smallest. Alright, so this is the idea to explain the question 3b. Now we're going to do tutorial question 4. So the removal and addition of electron results in a change of the atomic radii. We need to explain the difference in radius between the ions and their respective neutral atom. So we need to compare the ions with its respective neutral atom. So this comparison is one thing, and this comparison is another thing. So we need to do two explanation for two different species. So first, we can say that sodium plus, which is the cation, will always be smaller than the neutral atom. And for the second species here, we can say that the anion will always be larger than the neutral atom. Okay, so this has been covered in lecture, and the answer is essentially similar. So here going to be just a revision. So for Na plus and Na, firstly you can see that the number of electron in Na plus species is 10 because usually it will have 11, but because it has donates 1 electron, so it's going to become 10. While Na, neutral atom, we're going to have 11. However, their proton number is still the same, which is 11 proton. Na plus will has one shell less, which is 1s2, 2s2, 2p6, which is the electronic configuration here. Meanwhile, the sodium atom will have the electronic configuration of 1s2, 2s2, 2p6, and 3s1. So it's going to have an extra shell. Thus, you can say that the effective nuclear charge, or the ZEF, of a cation, which is the Na plus, is larger than of its neutral atom. Because when you look into the ZEF of Na plus, which is calculated by Z minus S, you know that the proton number here are going to be similar, which is 11. But the number of electron in the inner orbital has only 2. So 11 minus 2 going to become plus 9. So the ZEF here for Na plus going to be plus 9. However, when you counted the ZEF for Na atom, which is neutral, when you calculated it by Z minus S, it's going to become 11, which is a proton number, and the number of electron in the inner orbital, which is all of this, going to become 10. And lastly, you're going to get the ZEF of plus 1. Okay, so Na going to have a charge of plus 1. Okay, and this is considered inner orbital because 3s1 is the outermost. In this case, Na plus, the 2 n equal to 2 is the outermost orbital. So this one is the inner orbital. So we only have 2 electrons in the inner orbital. Okay, so as what you can see here, Na plus will have plus 9. Na atom will have plus 1. So the force of attraction in Na plus will pull the valence electron towards the nucleus stronger and hence make the size smaller. And as a result, the size of Na plus is going to be smaller than Na. Alright? And for Cl minus and Cl, you can see that the Cl minus is going to be larger than Cl because when the anion receive 1 electron, it's going to have a configuration of 1s2, 2s2, 2p6, 3s2, 3p6. Meanwhile, for the neutral atom, Cl, it's going to have a configuration of the similar one, but then 3p5. Okay? And the electron-electron repulsion in Cl minus will causes the electron to spread out more and experience less attraction from the nucleus because it receives extra electron. Okay, so the extra electron will spread the electron even more and causes it to be larger. And you know that the nuclear charge remains the same, which is the proton number, and this allows the electron to be pushed apart and the electron cloud enlarge. And as a result, the size of the Cl minus is going to be bigger than chlorine neutral atom. Okay, so that's all for question 4. So now for question 6, the table below shows the data for the successive ionization energy for the 3 elements of X, Y, and Z. So here are the data that are been given. So for question A, we need to predict the group for X in the periodic table, and then we need to give the reason. So the element X here will have the ionization energy as shown here. So as what you can see here, the energy gap or the huge gap can be seen in between the fourth energy level, the fourth ionization energy and the fifth ionization energy. So you know that from here, the fifth electron is removed from the inner shell or inner orbital. Okay, so there are going to be 4 valence electron. Okay, and you can imagine it to be something like this, which is 1, 2, 3, 4, and then it's going to have another electron in the middle here. So to remove the first electron is easy. The second electron going to be a little bit harder, increasing, a little bit harder, and then a little bit harder. So it just increase almost on a consistent increasing level. However, for the fifth electron, which is in the middle, which is closer to the nucleus, it will have a tremendous amount of energy. So you know that the fifth electron is from the inner shell. So from here, you can know that it will have 4 valence electron, and hence the group going to be group 14. Okay, and for the ionization energy, it can be only be applicable for S block and P block. So for the S block, it can only be group 1 and group 2. Meanwhile, for P block, going to be group 13, group 14, up to group 18. Okay, so D block is not applicable for this method for the ionization energy. So you only be dealing with 2 block, S and P block. So when you have 4 valence electron, it refers to group 14, not group 4. Okay, so be careful of that. So give your reason. So we can say that there's going to be a sudden increase in ionization energy between IE4 and IE5, and this shows that the fifth electron is removed from the inner shell, and therefore the X has 4 valence electron, so it belongs to group 14. You can also do the method 1 and method 2, where you can find the ratio, energy ratio, or you can find the energy difference. So if you want to do this way or this way, is also acceptable. And for question B, we need to write the valence electronic configuration of Z. Okay, so in order to write the valence electronic configuration, we need to know how much is the valence electron first. And in order to do this, we need to identify the biggest energy gap. So what you can do is you can find the ratio of IE2 divided by IE1 and so on and so forth. And for me, I will expect it to be at here because I can see that the energy gap from 1000 to 7000 is quite large. So I know that it's going to have 2 valence electron. Okay, and for if you want to prove yourself, you can use the energy ratio method, or you can find the energy difference, and you're going to see which one going to give you the highest amount. So the highest amount refers to the energy, refers to the electron that are in the inner shell. Okay, so for me, I will look into here. So I know that the third electron going to have the highest energy gap, which is 7730. So it's going to have 2 valence electron. Okay, so the first 2 electron is easy, but the third electron is difficult. So I know that it is in the group 2 because it has 2 valence electron. And as a result, it can be converted into the electronic configuration of NS2 because I don't know the period here. So I can just say that the electronic configuration of Z going to be NS2. Now for question 7, the graph below shows the variation of ionization energy for element Z. We need to state the group and the period of element Z. So as what you can see here, this is all the electrons for element Z. Okay, So the first 3 electrons, as what you can see, 1, 2, and 3 here, can be removed quite steadily. However, when it wanted to remove the 4th electron, the energy gap here is quite high. So there's going to be a sudden increase in the energy, in the ionization energy. So you know that they're going to be 3 valence electron. Okay, so you can imagine it to be 1, 2, and 3 valence electron. And then in the middle, you're going to have 1, 2, 3, 4, 5, 6, 7, 8. So another 8 electron in the inner shell. And then they're going to be another jump or another increase in energy, which shows that another 2 electron is in the inner shell, which is the most innerst one. Okay, and if you were to count the electron, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, and 13. So if you were to write it in the reverse way, you're going to get 2, 8, 3. So similar thing that you have learned in your high school, which is 2.8.3. Okay, and we're going to remove the 3 first, and then the 8 part, and then the 2 part, which is the last one. Okay, but in matriculation, we're going to write it in terms of SPDF notation, which is 1s2, 2s2, 2p6, 3s2, and 3p1. So similarly, it's going to become 2, 8, and 3. Okay, so the diagram here is just for visualization. So for this part, we need to state the group and the period for element Z. So the group, we know that it has 3 valence electron, and we're gonna plus with 10 because ionization energy can only happens for matriculation level, it can only happen for S block and P block. So we're gonna add up with 10, so it's gonna be group 13. And for the period, the highest, we're gonna have the 3 orbital, right? Or the principal quantum number, the highest is 3. So we know that it is in period 3. So we can say that it is in group 13 and period 3. So for the next question, why a higher energy is needed to remove the 4th electron? So you know that the 4th electron is removed from the inner shell. So the 4th electron is removed in the inner shell, which is closer to the nucleus. The attraction between the 4th electron to the nucleus is much stronger, and hence more energy is needed to remove the 4th electron in comparison to the valence electron, the 3 valence electron out there. Okay, and now we're going to state the oxidation number of element Z. So the oxidation number of element Z means that we need to make the atom stable. So for the ionization energy to occur effectively, it needs to remove electron so that the atom can become stable. So you know that you have 2 and 3. So logically, in order to become noble gases, it need to become 2.8. Or you can say that it's going to remove 3s2 and 3p1 so that it can get noble electronic configuration, which is neon. And as a result, it's going to remove 3 electron, which is 2 and 1. And as a result, you're going to have the oxidation number of 3 plus, which is plus 3. Okay, so if you write it in terms of like this, is acceptable. Or when you write it in terms of numbers only, you put as 3 plus. Okay, so either one of this. Okay, now for question 8, which element has the higher first ionization energy? So between magnesium or sodium, which one going to be having higher first ionization energy? What do you think? Yes, magnesium. So magnesium going to be having a first ionization energy, which is higher than sodium, because you know that the magnesium has a smaller atomic radii than the sodium. So sodium, magnesium. So as it goes across a period, the proton number increases and the ZEF increases as well. So more energy is required to remove one electron from the magnesium, which is smaller in atomic radii than the sodium. And that is why the magnesium first will have the higher first ionization energy. And for question B, oxygen and sulfur. Which one going to have the higher first ionization energy? Yes, the answer is oxygen. So oxygen going to have the higher first ionization energy because oxygen is located, both are in group 16, but oxygen is in period 2, but sodium is in period 3. Okay, so oxygen going to be smaller in size. So you can say that oxygen has a smaller atomic radii than sulfur, where the oxygen has the principal quantum number n equal to 2, while sulfur has n equal to 3. So since sulfur has more electron, so it's going to have a stronger shielding effect. And as a result of that, more energy is required to remove the first electron from the oxygen, which is smaller in size than sulfur. And that is why oxygen going to have the higher first ionization energy. Okay, and for C, in between nitrogen, oxygen, which one gonna have the higher first ionization energy? Okay, maksudnya elektron yang pertama dikeluarkan. Siapa yang mempunyai ionization energy yang tertinggi? So many of you may answer oxygen because you may think that oxygen is smaller, therefore oxygen will have the higher ionization energy. But this is incorrect because as what you have learned, this is known as the anomalous cases, where the anomalous cases happen in group 15 and group 16, as well as in group 2 and group 13. So you know that the nitrogen here will have a 2p3 half-filled orbital, which is for nitrogen, you're going to have 7 electrons, right? So it's going to become 1s2, 2s2, and 2p3. So the 2p3 here is a half-filled orbital, which is much more stable than the partially filled orbital of oxygen. So that is why to remove first electron from the 2p3 is very, very difficult, and it requires more energy. And hence, the first ionization energy for nitrogen going to be higher than oxygen. Okay, so the answer is N. N has a more stable half-filled 2p orbital, which is, as mentioned, 2p3, while oxygen has a partially filled 2p orbital, which is 2p4, if you were to count that. So removing an electron from the half-filled p orbital in nitrogen make the atom less stable, which is unfavorable process. Thus, more energy is needed to remove the first electron from the nitrogen atom. Alright, so that's all for question 8. So now for tutorial question 10, the table 1 shows the position of elements P, Q, R, S, and T in the periodic table. So we need to state the proton number for the element Q here. So in order to state the proton number, we need to know the number of electron. So the number of electron can be obtained when we write out the electronic configuration. So from here, you know that the period gonna have period 3. So your n here should stop at 3. So when we write out the electronic configuration, we're gonna get 1s2, 2s2, 2p6, 3s, because it is in group 1, so it's gonna stop at 1, 3s1 here. Okay, so you can check back, which is your period is equal to 3, and then your block gonna be at S block, and then your group gonna be group 1 because it has 1 valence electron. So you know that the total number of electron gonna be 11 electron. And in the neutral state, the number of electron and proton should be the same. So when you have 11 electron, you're gonna have 11 proton as well. So the answer is 11. And for question B, which of the elements has the greatest metallic character? Okay, so for the metallic character here, we know that the metallic character is on the For example, this one is the staircase. Sorry. So it's on this part here. So the metallic character basically shows of how well it can donate electron or how electropositive it's gonna be. So the tendency to the higher the tendency to donate electron, the higher the metallic character. Okay, so amongst all these elements here, we need to find out which one can donate electron more effectively. So for me, I can see element Q and element T can donate electron effectively because they are in group 1. For group 15, 16, it usually receive electron. So it's either mine plus receive 3 electron or receive 2 electron to become stable. And this one usually donate, and this one usually donate. And for group 14 here, it usually receive or it can either receive or donate 4 electron. Okay, so to answer question B, we can only have two options, which is Q and T. So both are in group 1. So Q is in period 3 and T is in period 4. So I know that T, which is lower, which is down the group, going to have a higher principal quantum number as has a larger atomic radii, and hence the force of attraction between the nucleus and the valence electron is much weaker. So it can donate electron much more easily. And for that reason, T will have the greatest metallic character because it can donate electron more easily. And then for question C, we need to arrange the element in table 1 in ascending order of the atomic size. Explain. So we have the elements. For example, P is in period 2. Okay, we can put it here. And then for Q, R, and S, they are in the same period, which is Q, R is in group 15, S is in group 16. Okay, N equal to 3. Here is N equal to 2. And for N equal to 4, we have element T. So from here, you can look into the principal quantum number first. So you know that T gonna be the biggest, okay, or the largest size, and and P here gonna become the smallest, okay, because the principal quantum number here is 2. So you need to determine Q, R, and S sizes, okay, and in order to determine the sizes between these three, it is quite easy because you know that across a period, the proton number increases. So when the proton number increases, the ZEF increases as well. And as a result, the size decrease. So S gonna be the smallest, followed by R, and then Q. Okay, so I can say that the size of P is smaller than S, smaller than R, smaller than Q, and smaller than T, where T gonna be the largest. Okay, so the way that you can explain that, you can say that the P is the smallest since it has only principal quantum number n equal to 2, or it has 2 shell or the least shielding effect. Meanwhile, S, R, and Q are in the same shell, which is n equal to 3. So S has a higher proton number, okay, has the highest proton number, and then it's gonna has the highest effective nuclear charge, followed by R and then Q. Okay, and that's the reason why we have the sequence here. And T gonna become the largest because it has the largest principal quantum number, n equal to 4, which has 4 shell and has the largest shielding effect. Okay, so this is how you explain and arrange the element in ascending order of atomic size. Now for question 10D, we need to give ions that are isoelectronic with argon. So argon is a noble gases, and the noble gases will have 18 electrons. So the electronic configuration is going to be 1s2, 2s2, 2p6, 3s2, and 3p6. which we have 18 electrons altogether. So we need to give ions that are isoelectronic. Isoelectronic means they have the same valence electron or the same number of electrons. So for this case, we have T here. We're going to have the electronic configuration of 1s2, 2s2, 2p6, 3s2, 3p6, 4s1. So for T, it can remove one electron in order to become the isoelectronic with argon. So T, the ions here are going to become T plus. Okay, for S, it needs to receive 2 electrons in order to become 18. Because you know that for S, you're going to have 1s2, 2s2, 2p6, 3s2, 3p4. So S here going to receive 2 electrons in order to become 3p6. Okay, and for R, similar thing, you're going to have 3s2, 3p3. The others is the same. So R going to receive 3 electrons in order to become 3p6. Okay, so this R, S, and T can become isoelectronic with argon. For Q and P, for Q usually we're gonna have 1s2, 2s2, 2p6, 3s1. So for this part, we usually donate 1 electron, and as a result, it's going to become 1s2, 2p6, which is not the same. And that is why Q isn't accepted, and P will also not be accepted because it is only have 2 principal, has only n equal to 2, which is very, very far away from 3. Okay, so the answer here going to be R3 minus, S2 minus, and T plus. And then for question E, we need to explain why the first ionization energy of R is higher than S. So similarly, as what you can see here, R going to have a half-filled orbital of the 3p. Meanwhile, S will have a partially filled orbital. And because the half-filled orbital is more stable, it is much more difficult to remove an electron from the R atom. Okay, so you can say that the R has a 3p half-filled orbital, which is more stable than partially filled 3p orbital in sulfur. In element S. Okay, so more energy is required to remove the first electron in R. Okay, and now we're going to list down the element in table 1 that will form acidic oxide. So acidic oxide here comes from the non-metal part. So the non-metal here refers to group R and S. Okay, so this one is the periodic table, and then we're gonna have including group 14, P, R, and S. So group 13 is here. This one is group 14, 15, 16, 17, 18. So this part here is the non-metal part. So the non-metal part gonna form acidic oxide when it reacts with oxygen. So the answer here gonna be P, R, and S. Alright. Now we're gonna look into the last question, which is tutorial question 11. So figure 2 shows a part of the periodic table. The position of 9 elements are indicated by letters not representing their usual symbol. And we need to answer the following question based on the figure given. So we need to identify the element which has the largest ionic radius. Okay, so again, look into the term here, ionic. So logically, the largest ionic radius will fall into this period, which is either G, H, or I. Okay, and we know that when we are talking about ions, it needs to be positive or negative. So usually, because G is in group 1, it's going to become G plus. And hydrogen, and for the H element here, it is in the transition element. So we cannot easily determine the charges, but we know that I gonna become I minus. Okay, so I minus gonna, when it receive one electron, it gonna have a more electron. So more electron means that the shielding effect gonna be increases. So the mutual repulsion between electrons causes the electron to be spread out and the electron cloud to be enlarged. And as the result, the I minus gonna appear larger than the corresponding G and H, because H here usually a positive charge for the transition element. For example, like zinc 2 plus, or maybe you can say copper 2 plus. So it's usually a cations, but anions will usually larger than the neutral atom at the cation. So that for that reason, the answer gonna be I minus. Okay, so because it says about element, so we just gonna put as I, and then has the smallest atomic radius. So the smallest atomic radius, we need to look into this period, which is n equal to 2. Okay, so here is n equal to 1, the second one is n equal to 2. So the smallest is B, because across a period, the proton number increases, the ZEF increases, and hence the sizes will get smaller. So now for the lowest ionization energy. So for the lowest ionization energy, we need to look into the largest atom. Okay, largest atom. So we are talking about atom now, eh? So atom, the largest gonna appear at this period here, which is n is equal to 4. So in comparison, G, H, and I atom, so I gonna become the smallest because proton number increases and effective nuclear charge increases. So I gonna be the smallest in comparison to G and H gonna become the largest. So when G is the largest, the electron is further away from the nucleus, and hence it's going to be easier to remove the one electron from the attraction between the nucleus. So as a result, the G going to has the lowest first ionization energy. And now for the highest electron negativity, the tendency to pull electron towards itself. So the smallest atom, this refers to a smallest atom, and the most logical answer in this figure here is B, which is fluorine. So as what you can see, this is the smallest atom because as you go across the period, the proton number increases, the Ceph increases, and therefore it is going to be the smallest and is easier to receive an electron. And for this reason, the highest electron negativity going to be B. And now for question E, forms amphoteric salt with oxygen. So amphoteric salt gonna refers to element in group 13. So the most logical answer, because this one is 1, 2, and then we have group 13, and then the most logical answer, we have only one element in group 13, which is D. So we know that the elements that are going to form amphoteric salt with oxygen is element D. Okay, so I think that's all for today's video. See you again some other time. Bye.